This lesson helps you understand inverse variation. A relationship represented by the function y equals k over x is an inverse variation, where k is the constant of variation, and k can be any real number except 0. Examples of inverse variation would be y equals 3 over x and y equals negative 2 over x. When x and y are related as an inverse variation, we say y varies inversely with x. Also, if you start with the function for inverse variation and multiply both sides by x, you get a new form of the function x times y equals k. This means if a pair of xy values is related by an inverse variation, their product is constant. In addition, notice if either x or y were equal to 0, the product would equal 0. Since the constant of variation can't equal 0, this means for an inverse variation, neither x nor y can equal 0. Here's an example of the kind of question you should be able to answer. Suppose y varies inversely with x. If y equals 6 when x equals 5, find the equation that relates x and y. Then, what's the value of y when x equals 10? Start with x times y equals k. Substitute y equals 6 and x equals 5. And you can see k equals 30. So the equation of inverse variation is y equals 30 over x. Then using the equation, substitute x equals 10, and you can see y equals 3 when x equals 10. The familiar equation rate times time equals distance can be an inverse variation. For example, if you walk a constant 5 miles each day, your rate or speed varies inversely with your time. Rate and time can vary, but their product is constant. You could walk 5 miles per hour for 1 hour, or 2.5 miles per hour for 2 hours, or 1.25 miles per hour for 4 hours. To get the function form of the inverse variation, divide both sides of the equation by time, and you have rate equals 5 miles over time. So if you wanted to make the 5-mile walk in 3 hours, your rate would be 1 2/3 miles per hour. Earlier in the lesson, we pointed out neither variable can equal 0. In the context of this example, that's easy to understand. With the rate of 0, it wouldn't matter how long, you wouldn't be able to walk 5 miles. Or with time equal to 0, it wouldn't matter how fast you move, you still wouldn't get anywhere. You can graph the function from a table of values. The function is not defined for t equals 0. For t equals 1, r equals 5. For t equals 2, r equals 2.5. For t equals 4, r equals 1.25. The function is also defined for negative values of time. Then draw a smooth curve through the points. You have a graph of the function. Notice the symmetry of the graph across the origin. We'll talk more about this function later, but for now, in the context of this example, only the part of the graph in the first quadrant is useful. Two more values have been added to the table. So it shows the inverse variation for time equals 1 through time equals 5. And you can see the graph tells the story. To walk a constant 5 miles a day, if you walk faster, it takes less time. If you walk slower, it takes more time. The graph curves upwards towards the y-axis, but it's not defined for time equals 0. The graph curves downwards towards the x-axis, but it's not defined for rate equals 0. So the function for inverse variation is y equals k over x, which is equivalent to x times y equals k. This means x and y are related by an inverse variation if the product of x and y is constant. From a previous lesson, you should recall the function for a direct variation is y equals k times x, which is equivalent to y over x equals k. This means x and y are related by a direct variation if the quotient of x and y is constant. So if you have a table of data pairs, you can determine whether they are related by an inverse or direct variation by finding the product and the quotient of each pair. For this example, since the quotient is constant, these values of x and y are related by the direct variation y equals 0.75 times x. For this example, since the product is constant, these values are related by an inverse variation y equals 18 over x. This lesson was brought to you by the Math Fun Academy. Its continuing mission: to explore strange new worlds, to seek out new math and new equations, to boldly go where no math student has gone before.